Hi, I'm William Spaniel. Let's learn some game theory. Today we're going to look at a game that has infinitely many equilibria, and that game will be this one right here. So if you want to try to figure this out for yourself, why there are infinitely many equilibria for this particular game, then you can pause the video right now. Otherwise, I will go ahead and solve it. So the first thing that you should notice is that for player 2, right is strictly dominated by left. And to see that, let's take a look right here. We've isolated player 2's payoffs, and we see that if player 1 plays up and player 2 has to decide between left and right, well, left is going to win because 2 is greater than 0. And likewise, if player 1 were to play down and player 2 were to decide between left and right, again, left would be better than right. This is because 3 is greater than -1. So as we've talked about plenty of times in the past, because left strictly dominates right, we can get rid of right from the game, and we can reduce the game to look like this. And we should see immediately that there are two pure strategy Nash equilibria here. The first one is up left, and the second one is down left. So essentially, both of the things that are left over here are going to be pure strategy Nash equilibria. And the reason for that is, well, let's look at player 1's payoffs. If player 2 is playing left, which we know she's going to do because left strictly dominates right, leaving left as their only strategy, well, if player 1 plays up, he'll get 2. He does not have a profitable deviation. That is, he can't switch to playing down and profit from this because he's going to get the same payoff. He's going to go from 2 to 2, which is not a profitable deviation. So up left is going to be an equilibrium. And likewise, down left is going to be an equilibrium because, well, if player 1 were playing down, he also does not have a profitable deviation to up for the same reason as before. If he were to switch to up, he would go from 2 points here to 2 points here, so this is not a profitable deviation. He's getting the same. So both of those are going to be pure strategy Nash equilibria, this up left and this down left. Now, it shouldn't take much convincing for you to understand that there are going to be infinitely many mixed strategy Nash equilibria here. That is, player 1 can mix between up and down with any probability, and player 2 will play left, and that is going to be a Nash equilibrium. And to verify this, let's take a look at what happens here if player 1 plays some mixed strategy sigma u. So some percentage of the time, he's going to get 2 points. That's this 2 right here from playing the up percent of the time, right? And then the rest of the time, so 1 minus the probability that he plays up, which is also known as the probability he plays down, he's going to get 2 points. That's this 2 points here. And if we do a little bit of algebraic manipulation, we'll see that this is always going to equal 2. So basically, no matter what player 1 does in equilibrium, he's going to get 2. So that means he doesn't have a profitable deviation, whether he's playing a pure strategy of up, a pure strategy of down, or any probability in between those two. So he could play up 50% of the time, down 50% of the time, up 75% of the time, down 25% of the time. It doesn't matter. You can literally take any probability distribution between up and down, and player 1 is going to be indifferent between playing that probability distribution or playing another one of those probability distributions or playing one of these two strategies as a pure strategy. And so that's why there are going to be infinitely many equilibria in mixed strategies here. Now you'll see this kind of problem come up frequently on problem sets, and now that you've had a little bit of experience with it, you've seen that there actually can be infinitely many equilibria in a game. I hope you will no longer be tricked by this. So good luck with those homework assignments.